On in Chemistry 40 land, it is Dr. Carroll with Lecture 4 on Unit 7, all about redox. And today we're going to use a textbook from out west in Canada because they have a real good section on electrolysis. I will email you the link so you can read it on your own, but I'm going to use it as a guideline here. This is it's chapter 17 in that book. It's an open stacks book. Anyway, so I'm just going to go through it, and hopefully you'll find some interesting things. We're going to see that electrolytic cells are different than galvanic cells, and we're going to look at some quantitative calculations and a bit of qualitative stuff as well. So recall that in galvanic cells, chemical energy is converted into electrical energy, like we find in a battery, for example. And the opposite is true for electrolytic cells. You need electrical energy to cause non-spontaneous reactions to occur. So you need an external source of energy to make something happen that otherwise wouldn't happen. That is what an electrolytic cell does. If you have an electric car, charging up the battery is an example of an electrolytic cell. Electrical energy is converted to the chemical energy in the battery as it is charged. Once charged, the battery can be used to power the car. Okay, so let's look at some examples. Here we have molten sodium chloride, which is different, by the way, than aqueous sodium chloride, right? Molten sodium chloride is going to be NaCl liquid. So you just heat the living daylights out of salt. You don't dissolve in water. If you dissolve it in water, that's aqueous. So let's see what we have here. In molten sodium chloride, the ions are free to migrate to the electrodes of an electrolytic cell. We have a simplified diagram used to produce sodium metal and chlorine gas by using electricity to break it apart. When you see the word lysis, it means breaking things apart in many cases. So sodium is a strong reducing agent, and chlorine is used to purify water and is used in antiseptics and in paper production. So that's all important. So here's some reactions. We have the 2-chloride at the anode, so that's got to be an arrow that's missing, right? Goes to Cl2 gas plus 2 electrons, and at the cathode in the electrolytic cell, sodium plus in the liquid phase, not aqueous, but in the liquid phase, goes to sodium liquid. So overall, the reaction is -4 volts. Okay, and you can say, whoa, we learned before in this chapter that a galvanic cell, the cell voltage has to be positive. So here it's negative, right? E0 cell is E0 cathode, so -2.7, -1.3, so -4.0. And that ain't going to happen unless we use a power supply, an external power supply like a battery or a generator, which has to supply a minimum of 4 volts, but usually higher because things are inefficient. And so what you're doing is you're pushing the electrons in the opposite way that they naturally want to go by having this external power source. And here's a picture. We see at the anode, we have the electrons are flowing, still anode to cathode, but the cathode here is Na plus, gobbling up in electrons to become Na liquid, and you're forming chlorine gas from chloride. Here's a hint. Whenever you see a picture in any area of science or economics or anything, read the figure captions. The figure captions are there for a reason. I remember way back when I did my PhD in, I think, 600 BCE, I had to make reams and reams of figure captions, and it was annoying, and it had to be on separate pages, and the word processing wasn't as fancy as it is today. And there's a lot of effort in figure captions, so always read them and understand them. So here's the figure. Passing an electric current through molten sodium chloride decomposes the material into sodium metal and chlorine gas. Care must be taken to keep the products separated to prevent the spontaneous formation of sodium chloride. Okay, and so here, rather than the salt bridge, they have a porous screen. So this is an example of an electrolytic cell. Electrolytic cell. Okay. If you did it in aqueous, it'll be a different story. I don't think we'll bother with that. Electrolysis of water. You can split water into hydrogen and oxygen gas. Into hydrogen gas and oxygen gas by electrolysis. Acids are typically added to increase the concentration of hydrogen ions in solution. It makes things happen more efficiently. So you have 2H2O, and that should be an arrow there. It goes to O2 plus 4H plus 4 electrons. So at the anode, we get oxygen formation, and at the cathode, the H plus gobbles up electrons, and we get hydrogen gas formation. That's the standard hydrogen electrode. So overall, if this were to happen spontaneously, it wouldn't happen spontaneously, right? Because it'd be cathode 0 minus 1.229, negative 1.229. So your power supply has to be more than 1.229 volts to make the oxygen gas and the hydrogen gas. And you're going to find, as you see overall, that you'll form twice the amount of hydrogen gas as oxygen gas. So note the sulfuric acid is not consumed. So sulfuric acid just helps us get the hydrogen gas formed. The volume of hydrogen gas produced is twice the volume of oxygen. You can see that here, just based on displacement. See where I have a space here, which it looks like nothing's there, but that is the hydrogen gas bubbling up. And here's the oxygen, and the oxygen looks around half of the hydrogen, right? So you have twice as much hydrogen gas formed as oxygen gas in that example. Okay? Let's read the figure caption. So water decomposed into oxygen and hydrogen gas during electrolysis. Sulfuric acid was added to increase the concentration of hydrogen ions and the total number of ions in solution, but does not take part in the reaction. The volume of hydrogen gas collected is twice the volume of oxygen gas collected due to the stoichiometry. Okay. The electrolysis of aqueous sodium chloride, that one I'm going to skip. I'm not going to, we can't look at every single thing here. You can certainly read that on your own. Now let's talk about electroplating, because that's interesting. Maybe some of you have family members, usually older family members, who collect spoons, right? Maybe from the World's Fair of St. Louis in 1916 or something, right? So you got the spoon, and then it is covered with maybe like gold, right? So it's gold covering of an iron spoon or something like that. And it's, oh, it's the greatest thing of all time. Or maybe some of you have Olympic medals and they're electroplated. So you have a medal on top of another one. So let's read through this. An important use for electrolytic cells is in electroplating. Electroplating results in a thin coating of one metal on top of a conducting surface. Reasons for electroplating include making the object more corrosion resistant, right? You know all about corrosion, eating away at things, strengthening the surface, producing a more attractive finish, right? Those nice chromium bumpers on your car, or for purification purposes. The metals commonly used in electroplating include cadmium, which is pretty nasty. I wish no one would use cadmium anymore. It's really nasty for the environment. Chromium, copper, gold, nickel, silver, and tin. Right? Well, if you could, you'd want sterling silver forks, right? If you can't get that, then silver-plated forks would be a really lovely wedding present, right? If you can't get that, then stainless steel, silver is good. And if you can't get that, hey, plastic forks will work. If you can't get that, just use your hands. There you go. The 5 steps. In fact, I should give that lecture in grand forks. Ha. Common consumer products include silver-plated or gold-plated tableware. We just said that. Gold-plated tableware? Really? I'm not going to use a golden spoon. Maybe you are. Chrome-plated automobile parts and jewelry. We can get an idea of how this works by investigating how silver-plated tableware is produced. Figure 3. Well, it doesn't show up, does it? Haha. Okay. Oh, wait. Maybe if I click on it. No, I'm not going to be able to click on it. But I'm going to give you the link, and I think it's because I'm in this presentation software that I can't see the picture. But I'll give you the link, or I'll just send out the photo to you so you can see it. So you're going to have a spoon is made of an inexpensive metal, is connected to the negative terminal of the voltage source and acts as the cathode. The anode is a silver electrode. They're both immersed in a silver nitrate solution. Silver nitrate is AgNO3. When a steady current is passed through the solution, the net result is that silver metal is removed from the anode and deposited onto the cathode. So the anode consists of a silver electrode, the cathode is the spoon. Both electrodes are immersed in solution. As you increase the potential, current flows, silver is lost from the anode, goes into solution as aqueous, and then at the cathode it deposits out onto the spoon. So the net result is the transfer of silver metal from the anode to the cathode. The quality of the object is usually determined by the thickness of the deposit of silver and the rate of deposition, right? You don't want it to take 4 years to coat a crappy spoon with silver. You want it to happen quickly, and you want it to be fairly thick. You don't want it to be so thin that your fingernail cuts through and then you see the lousy tableware underneath. Okay, so cool stuff. Quantitative aspects of electrolysis. Quantitative, when you think of quantitative, you think of numbers, right? So the amount of current that is allowed to flow in an electrolytic cell is related to the number of moles of electrons. The number of moles of electrons could be related to the reactants and products using our friend stoichiometry. The SI unit for current, and all you physics people know this, and I taught lots of you physics, I is the ampere, which is the equivalent of 1 coulomb per second. So the total charge now in physics, we often use lowercase q, but we can use uppercase q as well. So q equals IT, which is the same as n times F. Okay. In my physics class, q equals IT, and the way I remember it is there's no quit. There's no u in quit because you don't quit, so you don't see a u in here. So it's just q equals IT. T is the time in seconds, n is the number of moles of electrons, F is Faraday's constant, which is around, they're going to tell us, I think it's 96,485 coulombs per mole of electron. Okay, and if you multiply that by n, the moles of electrons, you'll get coulombs, just like I times T is coulombs. So all the units make sense. Okay, let's look at some examples of how this works, and I'm just going to write it here again. So I times T equals n times F equals Q. These are our equations, and how does it work? In one process used for electroplating silver, a current of 10.23 amps was passed through an electrolytic cell for exactly 1 hour. How many moles of electrons passed through this cell, and what mass of silver was deposited on the cathode? Okay, so we want to get start with the moles of electrons. So N, well, I guess it's worked out here, so I'll just look at it. So N equals Q over F. Q is I times T, so it's 10.23 amps, and amp is a coulomb per second times 3600 seconds, right? 1 hour times 60 minutes per hour times 60 seconds per minute. So that's going to give me the coulombs in the numerator, and then I divide by the Faraday's constant in the denominator, right? N is Q over F. I know that from here. N equals Q over F. So Faraday's constant is coulombs per moles of electrons. So the moles of electrons cancel, and you get 0.3817 moles of electrons. I don't know why this little backward slant is there. I'm going to get rid of that. So 0.3817 moles of electrons. From the problem, the solution containing silver nitrate. So the reaction at the cathode involves 1 mole of electrons for each mole of silver. So Ag plus, for every mole of Ag plus that becomes Ag solid, 1 mole of electron is needed. So if 0.3817 moles of electrons are poured into the solution, 0.3817 moles of silver solid are formed. Okay, again, why is this? The lovely font substitutions, right? You gotta love these things. So the atomic mass of silver is 107.9 grams per mole. So 0.3817 817 moles of electrons times the molar mass of silver, 107.9 grams per mole. So the moles of electrons cancel, and you get 41.19 grams of silver. And you see that if we ran the current for a greater length of time, more silver would come out, right? Because Q is I times T. So if we did it for 2 hours, guess what? We'd have twice as many grams of silver being produced. And if the current was larger, we would proportionally get more silver produced. Okay. So that's good. What's this? Check your learning. Oh, I like learning. Aluminum metal can be made from aluminum ions by electrolysis. What is the half reaction at the cathode? The half reaction at the cathode, okay, it's called cathodic reduction. That's a word you may see in some other textbooks. Cathodic reduction. So aluminum 3 plus gobbles up 3 electrons to become aluminum solid. And we're passing in 2500 amps through a solution in 15 minutes. Assume the yield is 100%. Oh my goodness, they don't tell us how to do this one. Oh boy, can we do it? We can try, right? So let's start by getting the moles of electrons, which is N, right? So N equals Q over F. Q is IT, so it's IT over F. I, how many? 2500 amps. What's the time? 15 minutes, so that's 15 times 60 seconds. Okay, because you have to be in seconds, so you end up with coulombs. And Faraday's constant, did they round it off to? No, 96.485. I sometimes think of it as 96,485 coulombs. Right, that's from the musical Rent, which some of you may be fans of. Everyone's fans of Hamilton, of course. 2500 times 15 times 60 divided by 96485. I'm doing this live right now. Isn't that exciting? 96485. 23.32 moles. Okay, of electrons. And then I see 1 mole of aluminum is produced for every 3 moles of electrons, right? That's what my balanced stoichiometry tells me. So I'm going to multiply that by 23.32 moles of electrons. So I get 23.32 divided by 3 is 7.7. 7.7, what is that? Moles of aluminum. Oh, what's the molar mass of aluminum? Is it 23? I don't know. I don't know the molar mass of aluminum. It's going to be 210. So let's store that. Let's do 210 divided by 7.7. 27. Yeah, that's right. That's right. Aluminum is around 27 grams per mole. So it gives you 210.0 grams. Is it really? Now I gotta just check this. I'm gonna go up here, open another tab. Oh, you're seeing all this, and I'll just type in Disney Plus. Oh no, I don't want Disney Plus. Oh, that's got Hamilton, doesn't it? Molar mass of cookies. No, molar mass aluminum. Going to be 27. I'm sure it's 27. What is it? 26.98. Oh, come on, that's 27. Good. Okay, that was exciting, eh? The suspense on knowing what aluminum was. Okay, so let's try another one. In one application, a 0.01 millimeter layer of chromium must be deposited on a part, maybe it's in a car, with a total surface area of 3.3 square meters from a solution of containing chromium-3 ions. How long would it take to deposit the layer of chromium if the current was 33.46 amps? The density of chromium metal is 7.9 grams per cubic centimeter. Okay, so this has lots of topics. And let's go through it. So let's solve in steps. And we want to start with what volume of chromium is required. Yeah, if I get the volume, I can go and get the mass. So volume is, let's see, 0.01 millimeter layer. That's my length. I'm converting it into centimeters. Then the surface area times the length is going to be the volume. So I got to convert the centimeters squared to meters squared. And I get 33 cubic centimeters, or 33 milliliters if we're talking about liquid. But solid, we like to use cubic centimeters. So that's the volume of the part that we want to coat with chromium. And then the mass is the volume times the density, and that's 237 grams of chromium. I divide by the molar mass, get 4.56 moles of chromium, and then I need 3 moles of electrons are required per mole of chromium, right? Remember what we're talking about, cathodic reaction. Cr3 plus 3 electrons goes to Cr. So I had 4.56 moles of chromium times 3 moles of electrons per every mole of chromium. So that gives me moles of electrons, and to get to coulombs, I just multiply by Faraday's constant. You see how you really don't need to know many equations. If you know the units for all these things, then you can really get going and get everything canceling out. It just takes more time, though, to write in all the units in the intermediate step. But you get 1.32 by 10 to the 6 coulombs, and you divide that by the current, 33.46 coulombs per second, and you get 3.95 by 10 to the 4 seconds. And if you want, you can convert that to 11 hours. So it takes 11 hours to coat this part. And I have a hunch here they're talking about a chromium bumper on a car. They don't say, do they? They just say a part, but that's what I'm guessing. Check your answer. In a long problem like this, a single check is probably not enough. Each of the steps gives a reasonable number, so things are probably correct, but pay careful attention to unit convergence and stoichiometry. Okay. You're going to try to check your learning if you want on your own. You have here, you want to galvanize. That means put zinc on top of something. When we talk about galvanized steel, that means it's protected with zinc, and zinc is the stuff that's going to oxidize. Galvanize the top of a sheet of iron to a thickness of so much millimeters of zinc. And so you can do the same kind of question. Okay. Key concepts in summary. Using electricity to form a non-spontaneous process to occur is electrolysis. Electrolytic cells are electrochemical cells with negative cell potentials, and so are non-spontaneous. And we'll talk about the Gibbs energy. Electrolysis can occur in electrolytic cells by introducing a power supply, which supplies the energy to force the electrons to flow in the non-spontaneous direction. Electrolysis is done in solutions, which you have to have enough ions so current can flow. If you don't, then current stops. Okay, I don't have to read all of this. Over potential, we won't get to that. Then we had some key equations here. Q equals IT equals N times F. And then there are some questions. Don't worry about one, but try what mass of each product? No, let's try 3. How long would it take to reduce 1 mole of each of the following ions using the current indicated? And that's good. 3 is good. Then there's a glossary, which is nice. Oh, look at that. There's even the answers there for you. Okay. For question 2 and question 4. For question 3, they are not there. So I guess we should try to do that. So let's just do that right now. So the first one, aluminum 3 plus 3 electrons goes to form aluminum. So how long would it take? So what's our equation here? Let me just go up here. And so T equals NF over I. T equals NF over I, where N is the moles of electrons. So there's 3 moles of electrons for every aluminum mole to go. So it's going to be 3 times 96,485 divided by the current, 1.234. I guess they don't give all the answers. They want you to do some on your own and then hand them in, and we've done that many times. Here, let's just do it together for fun. And you get, second scientific notation, in seconds, 2.35 by 10 to the 2.346 if you want to be a sig fig meister. 2.346 by 10 to the 5 seconds. The next one, calcium 2 plus 2 electrons goes to form calcium. So the time is N. Here we're going to have 2 moles times 96,485 over the current 22.2. So 2 times 96,485 divided by 22.2 is going to be 8.69. That's 3 sig figs. 8.69 by 10 to the 3 seconds. That's a 9. Chromium 5 plus? Are you kidding me? Really? Well, there you go. Chromium 5 plus. So that's going to need 5 electrons to form chromium. So times, we're going to have 5 times 96,485. Chromium 5 plus, really? 37.45. That's, I guess in some compounds you can get that, but not that common. In most of the questions we look at, 37.45, 1.2, here's you got 4 sig figs, 1.288 by 10 to the 4 seconds. And finally, we got AU 3 plus 3 electrons goes to form AU. So the time is N. So 3 times 96,485 over I, 3.57. And you get 8.11 by 10 to the 4th seconds. So that's electrolysis, and there's lots more fine details about it, but I think we'll leave that for now. Okay, hope you enjoyed this.